Let's talk about graphing logarithmic functions. Before I graph a logarithmic function, I want to go back and review graphing an exponential function. So just really quickly, let's sketch the graph of f of x equals 3 to the x. And if you watched my video on how to do this, we did this by pretty simply plotting points. X and y equals 3 to the x. And the 3 points I'm very fond of picking are the points when x is 2, x is 0, and x is negative 2. So let's see, when I plug in x equals 2, 3 to the 2 gives me 9, so I have the ordered pair 2, 9. When I plug in x is 0, 3 to the 0 is 1, I have the ordered pair 0, 1. And then finally, when we plugged in negative 2, we got 1/9. 3 to the negative 2 is 1/9. So when x is negative 2, y is 1/9. So if I plot these on my graph over here, I have x is 2 and y is 1, 2, 3, 4, 5, 6, 7, 8, 9. I have x is 0 and y is 1, and x is negative 2. Ooh, that's pretty tough. And y is 1/9, and I have this horizontal asymptote there along the y-axis. Along the x-axis along y equals 0. All right, now remember, in the previous video on the intro to logarithmic functions, a logarithmic function was obtained by finding the inverse function to an exponential function. So we had f inverse of x is log base 3 of x. And if I were to graph log base 3 of x, I don't want to pick 2, 0, and negative 2 because I don't have a calculator with me. And a couple of those are going to give me no solution. So I'm going to pick for x some values that are similar to base 3's. So I'm going to pick a 9 and a 1/9. And I'm also going to pick a 1. And I'm picking these intentionally because 9 is 3 to the 2 power. So 9 is a 3 squared. Okay, watch what happens when I pick these. So I've got log base 3 of 9, log base 3 of 1, and log base 3 of 1/9. Okay, now in the last video we practiced evaluating these without a calculator. So log base 3 of 9 means what's the exponent I put on a 3 to spit out a 9? Well, 3 to the 2 is equal to 9. So I must have the ordered pair 9, 2 on that. Let's see, for the second one, what's the exponent we put on a 3 to get 1? Oh, well, anytime you put 0 as an exponent, you're going to get out a 1. So my point is 1, 0. And then finally, what's the exponent you put on a 3 to make 1/9? Oh, that is negative 2. So I have the ordered pair. I can't write right there. You might not see this, but I can. 1/9 and negative 2. Okay. Remember, that isn't very surprising because the main way of going from a regular function to its inverse was that you switch the x's and y's. So if the ordered pair 2, 9 is on the regular function, the ordered pair switching the x's and y's is on the inverse function. If the ordered pair 0, 1 is on f of x, the ordered pair 1, 0 is on f inverse. And finally, if the ordered pair negative 2, 1/9 is on the regular function, 1/9 negative 2, switching the x's and y's, is on the inverse function. When I go to plot these graphically, here's what I get. 3, 4, 5, 6, 7, 8, 9, 2. So there is 9, 2. When x is 1 and y is 0 is right here. And then when x is, ooh, that's going to be hard to plot, 1/9, and y is -2, that's here. So to the best of my ability, I'm going to draw that graph. I have an asymptote now along the y-axis. I'll make my dot a little bit bigger here. And the red graph is the graph of the log function. So one more quick point I want to make here after plotting those points. The big goal of finding an inverse function was to switch your x's and y's. And you can do that algebraically, like we did on those videos where we found inverse functions, just algebraically switch the x's and y's. You can do it with ordered pairs. X and y get switched from the regular function to the inverse function. And you can do it graphically. So graphically, switching your x's and y's creates a reflection around the line y equals x. So the blue curve and the red curve are reflections of one another around the line y equals x. Let's graph another logarithmic function that's a little bit different than log base 3 of x. For our next example, let's graph log base 5 of x, and let's not worry about its inverse function, which is 5 to the x. So I'm going to be carefully picking some x values that make my logarithm easy to calculate without a calculator. One x value I can always pick is 1. But for base 5, I could pick a 5 and a 25. And then the last one that's really helpful to pick is a 1/5. So anything that has a base 5 is a great choice for plugging in for log base 5. So let's plug these in and calculate them. Log base 5 of 1, that should always be something that's easy to calculate. What's the exponent we put on 5 to make 1? That's a 0. So when x is 1, y is 0. 5. Log base 5 of 5. What's the exponent we put on a 5 to keep it a 5? 5 to the 1. So 1, 2, 3, 4, 5. When x is 5, y is 1. 25. Log base 5 of 25. What's the exponent we put on a 5 to turn into a 25? That's exponent 2. Oh, that's really big. 25 is over here, let's say. Not quite to scale. Ooh, that's climbing very slowly to y equals 2. So definitely it's slowly going up to the right. And on the left portion of the graph, log base 5 of 1/5. Okay. How do I make a 5? What exponent do I put on a 5 to make it a 1/5? Make it a negative. Now it's going to be difficult to plot. X's 1/5 is here, as -1 for the y's goes down here. So these logarithmic graphs have asymptotes right on top of the y-axis, and they go like that, up and to the right. Okay, let's do one more graph, and then we'll talk a little bit about domain. Let's graph f of x equals negative log base 5 of x plus 2. Okay, so we're going to do this by making a chart, and I put parentheses here around the x just so that we could tell that the x is the only thing inside the argument of the log. The plus 2 is separate from that. Okay, I'm going to very carefully pick some x values here. Since we have log base 5s, I'm going to pick things with a base of 5. So always safe to pick 1, usually safe to pick 1. Let's pick 5 and 25, and then let's pick 1/5. Okay, so plugging in x equals 1, we have negative log base 5 of 1 plus 2. Let's see. So any log, a log with any base, I should say, of 1 is always equal to 0. So this will be 0 plus 2, which is 2. So when x is 1, y is 2. Okay, when x is 5, negative log base 5 of 5, and then plus 2. Okay, so starting from the inside out, the logarithm. What's the exponent we put on a 5 to keep it a 5? That exponent is a 1. So this becomes negative 1 plus 2, which is 1. Okay, so when x is 5, 2, 3, 4, 5, y is 1. 25. Holy cow. Okay, when x is 25, negative log base 5 of 25 plus 2. So again, doing the logarithm because it's on the inside first. Log base 5 of 25 is the exponent goes on 5 to make it a 25. That's 2. So we have negative 2 plus 2, which is 0. So x is 25. I'm going to exaggerate. We have 0. And when x is 1/5, negative log base 5 of 1 over 5 plus 2. Okay, so doing this again first, the exponent that goes on 5 to make it a 1 over 5 is negative 1. So this will be negative 1, which will be 1 plus 2 is 3. So when x is a little 1/5 right here, we have y is 3. Great. Now we have a really good picture of what our graph looks like. We clearly have an asymptote, as usual, along the y-axis, or a vertical asymptote. And pretty decent graph of what that looks like. And then the graph is going to go up on the left-hand side and down on the right-hand side instead of the usual. And that is due to this reflection here. One thing to point out, you might remember that a plus 2 on the outside will move our graph up or down. Sliding that graph that has a horizontal or a vertical asymptote rather up and down isn't going to change where that asymptote occurs. So that won't affect the asymptote. I want to talk about one more topic while we're looking at a graph, and that's the concept of domain. So I want to point out when we were picking all of these x values here, notice that I was picking only positive x values. And that makes sense once we look at the graph because we see that the x's are always on the right-hand side of our graph, and we have an asymptote. We don't have any x values over here. Well, when you have x values that you can plug in or not plug in, as the case may be, that entirely relates to domain. So let's look at some examples. So as a first example, let's consider the function f of x equals log base 2 of x. And what I'd like to do is pick a variety of x values as if I were to go graph it, but really I want to look for x values that can or cannot be plugged in. So let's see, if I were to graph this, some helpful x values, 1 is always, seems to be, I should say, always fine. Since we have log base 2 here, then anything that would be 2 to a certain power would be great too. So like a 2, a 4, not a 6, but perhaps an 8, and then even a 1 over 2. And because it's good practice, let's plug some of these in. So log base 2 of 1, what's the exponent that goes on a 2 to make it a 1 is 0, totally fine. When x is 2, log base 2 of 2, what's the exponent that we can put on a 2 to make a 2? Well, that's a 1. No problems here. When x is 4, What's the exponent you put on a 2 to create a 4? You put 2 to the 2 power. And when x is 8, that's the exponent you put on a 2 to make an 8. Oh, 2 to the 3. So that would be a 3. Again, these are all good. And even if it's a fraction, log base 2 of 1 over 2, what's the exponent I put on a 2 to make it a 1 over 2? I put a negative 1 exponent on there. Now watch what happens when I pick something like, instead of, let's say, 8, let's say I picked negative 8. What's the exponent I put on a 2 to make a negative 8? 2 to what exponent is negative 8? Well, it certainly can't be 3 because 2 to the 3 power is positive 8. It can't even be negative 3 because 2 to the negative 3, as we've been discussing, is 1 over 8, not negative 8. In fact, there's actually no way that we can take a positive number like a 2, raise it to some exponent, and pop out a negative result. So the arguments inside the logarithms must always be positive numbers. I want to try one more value. I would like to try 0. That's a really common number to plug in. So let's plug in x equals 0 because we've just figured that we can't have negatives inside our logarithms. What if we had log base 2 of 0? So that's asking the question 2 to what exponent spits out a 0? Well, it's certainly not 0 itself, right? 2 to the 0 power is 1, not 0, so that's not the problem. A positive would just give it a big number, and a negative would make it a fraction if it were in the exponent. So this is not possible, excuse me, and this is not possible. So the main idea when we're looking at domain, the main idea for logarithms is that the argument inside the log with any base has to be a positive number. The logarithm inside the log, the argument, inside the log for any base has to be a positive number. So if I'm looking, for example, just to find the domain of something as simple as log base 2 of x, in order to find that domain, very similar to when we find the domain of square root functions, we take just the argument, just the x, say it has to be positive. Unlike in the square root function though, this argument cannot be equal to 0, so we do not put an equals to 0 underneath, and then generally we write that once it's isolated for x in interval notation. So the domain for this function here would be x's from 0 to infinity, but not including 0. And one reason that domain is really helpful is here in blue, when I'm creating my graphs, I want to make sure that I'm only selecting x values that are in the domain. If I select x values that are not in 0 to infinity, then I'm going to get no solution. So let's try some more complicated looking functions with logarithms and finding those domains. Okay, let's find the domain for the function f of x equals log base 3 of 2x plus 12. So when we're finding domain, these are just what x values can we plug in or not. We're going to take the argument. We're going to ignore the base, take the argument, the 2x plus 12, and set that strictly greater than 0. So just take the inside, I'll highlight that. Just take the inside of the logarithm, the argument of the logarithm, and set that greater than 0. And then all we have to do is isolate x. 2x is greater than negative 12, so x is greater than negative 6. So my domain is negative 6 to infinity. So in this case, I actually could pick some negative x values and plug them in. And because of the plus 12 inside the parentheses there, I'll be okay. Let's do another one. Let's do find the domain for g of x. Let's make it a little bit harder. Let's do log base 5 of x squared minus x minus 12. Okay, so if we're just asked to find the domain, we only have to look at the argument, x squared minus x minus 12, and set that strictly greater than 0. So just look at the argument, and that is strictly greater than 0. A little bit of review here. Remember, to solve these are nonlinear inequalities. You factor these, x minus 4 and x plus 3. And when I teach how to solve a nonlinear inequality like this, I have boundary points, which are 4 and negative 3. And I plug in test values to the right and left of each of those boundary points. So very quickly plugging in x equals like negative 5, we would have negative 9 times negative 2, which is positive 18, which is definitely bigger than 0. So this would be true. When x is 0, I'm going to make this red. That's in between negative 3 and 4. I have negative 4 and positive 3 is negative 12, which is not bigger than 0. So that is a false column. And when x is something like, let's say 10, anything bigger than 4, we have 10 minus 4 is 6, and 10 plus 3 is 13. And whatever that is, it's the product of two positive numbers. So this is definitely going to be something positive is bigger than 0. It's definitely going to be true. So the answer here will be our true columns, this one and this one, which is negative infinity to negative 3 and 4 to infinity. You can probably tell the difficulty level took a turn from just a quick linear inequality where we isolate the x to something where we have to do, we call these sign charts. We have to do a sign chart and figure out which columns make the inside, in this case, positive. So let's do one or two more examples. Let's find the domain for h of x is equal to ln of x minus 2 over x plus 1. Okay, so remember the base doesn't matter. We do the domain for each of these the same way, and it's just the argument inside the logarithm that we're concerned with when we find domain. So to find the domain, we're going to take the x minus 2 and the x plus 1 and set that argument strictly greater than 0. Now don't multiply both sides by the x plus 1. That gets really confusing. This is really similar to the previous problem we did. We have boundary points, or critical points they're sometimes called, x equals 2 and negative 1. And just like in the last problem, I'm going to plot them on my number line. I'm going to pick points within each set. So maybe over here, negative 5, and way over here, positive 5, and then maybe in the middle, 0. And when I pick these and plug them in here for the x, negative 5 minus 2 is negative 7. Negative 5 plus 1 is negative 4, which is positive 7 over 4. And I'm looking for if that's positive, greater than 0 or not, and it is. So that is a true statement. However, when I plug in 0, I have 0 minus 2 over 0 plus 1, which is negative 2 over 1. That is not greater than 0. So that column gives me all false responses. And then finally, when we plug in 5 minus 2 over 5 plus 1 is 3 over 6. I know that's 1/2, but I care more about is it positive or not, greater than 0, and it is. So this is another true column. So this would be the column on the far left, negative infinity stops at -1. That's our true column. And the other true column is 2 to infinity.